Hi, today as part of our review video for this week, I'm going to be talking about binary search and why it's useful, logarithmic runtimes and what they are, and I'm going to go over problems 2a and 2b from section that you probably didn't have time to get to. Also, I'll do an algorithm analysis problem because those are really important for this class. Maybe important for tests. We'll see. So, what is binary search? Well, let's say we had a list of sorted numbers, or really any items, but I'm going to use numbers. So we have 9, I believe 9 items here. So intuitively, how are you going to search for, let's say, the number 21, which would be at index 7? Number 21. Well, you could just say, hey, I'm going to start at the first item. Is it 21? No, it's not. Go to the next one. Is this 21? Nope. And then go here, sorry about this, here, until finally you get to here. And that's what you want to do. And maybe your function will return the index of where you found 21. Now, this is guaranteed to work, and it'll also tell you if the item doesn't exist in the list. This is guaranteed to work, but as in this case, we have to traverse almost the whole list to find our answer. What if our list was 10 million items long, and our item is at the very end of the list? We'd have to search the whole list in order to find our item. That seems pretty inefficient. This is a n runtime. Well, how can we do better? How can we take advantage of the fact that this list is sorted? In fact, there's a neat trick we can do to do that. So let's say we start at the middle. In this case, our middle is 8. Now, we're trying to find 21, right? Is 8 less than, equal to, or greater than 21? Well, we know it's less than. And since this array is sorted, that means that everything to the left of 8 is going to be less than or equal to 8. And since 8 is less than 21, that means all of this is also less than 21. So we can get rid of this entire area. There's no way that anything in this area can be 21, because we know they're guaranteed to be less. So we've just eliminated half of our data, but we still haven't found our item. So now we have this subarray to search through. Now, at this point, it's up to you as a code designer to say, oh, I consider when my array is even, the left middle index to be our middle, or the right one. I generally do left, but it doesn't really matter. So in that case, with saying that, this would be our middle index. Is 20 equal to, less than, or greater than 21? It's less. So again, that item and everything to the left of it can be deleted from our search. And now we would move here, and now we've found 21, so we're done. That only took 3 operations, and as opposed to going the whole thing. Now, how much faster is this? What function is this? Well, I can describe it to you another way. Let's pretend that March Madness happened. I'm pretty sad it didn't. You start with 64 teams in here in round 1. Round 1, that's this round. You've got 64 teams trying to win the title. Now, every game, there's going to be somebody that loses and is knocked out. So we're actually getting rid of half of our teams. And that goes to round 2, which has 32 teams. And then round 3 is the round of 16. Round 4 is the quarterfinals with 8 teams. Round 5 is the semifinals with 4. And round 6 is our final game with just 2 teams left. That'll be our last game. So 6 rounds have been played. Why is the number 6 relevant? Well, it turns out that log base 2 of 64 teams, which is how many we started with, is equal to 6. That means if we keep dividing 64 by 2 again and again and again until we reach 1 team remaining, that means we're going to have 6 rounds of basketball games until we crown a champion. Now you could extend this and say if we started with 128 teams, we would have 7 rounds. That's what a logarithmic function really is. It tells you how many divisions by the base it takes you, or how many multiplications of that base it takes you to get to your desired number. A little bit more formal of a math definition is here. You may have seen this in your math class. It kind of this part is kind of what I was talking about. Now, logarithmic functions are really, really good in computer science. They're really, really fast and much, much faster than O of n, a linear function. If you can get a log function for any sort of function that you're making, generally it's going to be considered good because it's just really fast in the real world. And also in this class and in computer science in general, when we say log, we're generally going to drop the base and just say assume that is log base 2. I know in math classes sometimes you assume log just to be 10 or e if it's natural log, but if you just see log n, assume it's log base 2 unless specified otherwise. So with this information, we can solve problems 2a and 2b from your section handout if you want to follow along. 2a says, true or false, in the worst case, finding an element in a sorted array using binary search is O of n, bounded by O of n. Well, let's run through an example. Now, worst case. What would the worst case be? Well, you could say that the worst case is maybe it's at one of the ends of the list, but I would say, for my handwriting, I would say that the worst case is if the item doesn't exist at all, which means you have to search and then just say, oh, I couldn't find it. How long does that take? Well, we've got 8 items here. We start at this index is our middle. Is 4 equal to, let's say we're searching for 9, sorry. We're searching for 9 in this list. Obviously it doesn't exist, but how long does it take until we're going to know that? Is 4 equal to 9? No, it's not. Get rid of this. Now we're here. Is 6 equal to 9? No, it's not. Get rid of this. Is 7 equal to 9? Nope. And then we're here. 8 is still not equal to 9. So now we've looked through the whole list. It took us only 4 iterations to look through the entire list and tell us that 9 is not there. Now, log base 2 of 8 is equal to 3. And obviously we did 4 iterations. But our number of iterations in the worst case is still going to be on the order of log, right? If you had 128 items, maybe you would have 8 searches, but 8 is still on the order of log of 128, and it's nowhere near n, which would be 128. So that means that in the worst case, it's always going to take log n time. Now, think about that. Does that mean that this statement is true or false? Well, O of n in the worst case means that as bad as your function can be, it's upper bounded by O of n. That's actually still true because log n is less than O of n. Now, is O of n a tight bound? No, it's not. You would really want to say that it's O of log n. But since this is still bounded within O of n, this is true, we can say that, therefore, this whole statement is true. I know that can be a little bit tricky, but hopefully that made sense. Now let's go to this problem. True or false, in the worst case, finding an element in a sorted array using binary search is omega of n. Now, as we know, omega is the lower bound, and in this case, it's the lower bound of the worst case. And as I just said in the previous problem, in the worst case, you're always going to have log n iterations. And log n, if it were bounded by this function, sorry about that, if it were bounded by this function, how long it actually takes should be greater than or equal to our omega. How long it actually takes should be greater than or equal to omega. But is log n greater than or equal to n? No, it's not. Therefore, it doesn't make any sense to have our lower bound be n. Maybe we could have a lower bound be log n or a lower bound be 1, but it can't be n because n is not less than log of n. So this statement is false because omega of n cannot be possibly a lower bound of a log n function. But O of n can be a upper bound for a log n function. O of n factorial could be an upper bound for a log n function. So that's why that one's false, and the other one was true. So let's do some algorithm analysis practice. So let's take a look at this function. We've got statements here, 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 and here. Now each of these statements is just one thing that it's doing. It's not calling another function that has its own runtime. It's just doing one operation. So I'm going to refer to each of these in the runtime being 1. So this is 1, this is 1, this is 1. 1 unit of something when you're calculating how long it takes. Don't worry about the numbers specifically. It'll make sense later. So we're given an n, and our outer loop runs n divided by 3 times. And I'm going to get rid of these so it's a little bit easier to see. This inner loop happens n divided by this. Everything that happens here is going to happen n divided by 3 times. And then we've got another loop. This is going to happen however many iterations this statement runs for. So it's going to be, so this is 1, it's going to be 1, which is that int counter statement, plus n over 3 times whatever this operation takes, times, you got 2 statements here. So this times 2. That's going to be the overall runtime of this function. Now, what are the number of iterations for this second, the inner for loop? Well, we start k is equal to n, go until k is greater than or equal to 1, and this part keeps dividing k by 2. That should sound familiar. Let's say we have an n of 64. So you would start at 64, then you go to 32, then you would go to 16, 8, and then 4, I'm running out of space here, and then 2, and then now you're at 1. You remember this? This is logarithmic. This inner loop, we'll say that's log n. So now we have enough to say what exactly our runtime is going to be. Now remember, in overall runtimes, we can get rid of constants because as n goes to infinity, they're really not going to make that much of a difference in how the function looks. So we'll get rid of this, and we'll get rid of the 1/3. So then this reduces to 1 plus n times, because like I said, everything, let me make this a little clearer, everything that happens within this outer for loop happens n divided by 3 times. So that's why it's n divided by 3 times this inner part. So we reduce that to n times log n. And as we also remember, when we have a function like this where 2 things are being added, the part that's larger is going to dominate the other part. Like if you had n cubed plus n, the n is not going to matter, it's just going to be n cubed. So that's similar here. We can get rid of this 1 and just say that our function is n log n runtime. And that's our answer. That's all I've got for today. Thanks for watching, and hopefully this made sense.